Welcome back to the second part of motion control with an RC servo and an Arduino microcontroller. That's basically where we left off in the first part. Card here, link in the description. We were able to control our servo in a manner that it makes a nice, smooth sinusoidal motion. In this second part, I will try to start and stop that motion in a controlled manner. Yeah, therefore we have these two rotary encoders with push button function on the board. And to change the speed or frequency of the motion as well as the amplitude. So let's get started. In the first part, I used this picture with a sine wave to explain things, but in the end, I always had to overlay this sine curve ruler to show you the cosine curve, because in the code we used the cosine instead of the sine wave. I've remedied that and have drawn you the same picture with the actual cosine curve. Remember, a cosine is just a sine, shifted by half pi or 90 degrees. So really basically the same function. Anyway, we wanted to start and stop our motion always at that point here, because there the speed of our servo is almost zero, or mathematically speaking, at one point it is exactly zero. Alternatively, we could start and stop, let's say, at this point here, where the speed is, of course, also very low, or mathematically speaking, at exactly 1.0. And of course, you remember the four quadrants, 1, 2, 3, 4 of the circle, 0 to 2 pi, where the cosine and sine functions are defined. And I've marked them here in the picture 1, 2, 3, and 4. Just keep in mind, if we have a look at the code later on, it's C++, so I start with 0, and internally in the code they are numbered 0, 1, 2, 3. And that's what controlled start and stop in real life looks like. So I push the button and we start moving. And I push the button again and we stop in the same position. That's up in the up position. And it doesn't matter when I push the button. I try to time that now. It always moves back into the top position before it stops. Where we have the lowest speed, or theoretically at one point, I mentioned it already twice, 0. That's really important in motion control because, and I let it run continuously now, if I stop the servo, just by cutting its power, and then I reapply power, bad example, let's try again. You saw that jerk? Oh, that was a good one. These are the high forces due to high acceleration when you suddenly change the speed. That's what all this sinusoidal stuff is about. Avoiding fast changes of the speed. Now let's have a look at the code. Now, I've changed absolutely nothing here in the declarations, but we are using now this volatile boot speed encoder switch, and the value of that variable is toggled each time the button is pressed. If you want to know how that works, watch again the video about debouncing these rotary encoders. Card here, link in the description. And that speed encoder switch is initialized to false. That's also a point to remember. Now in the loop, I'm now using that static bowl speed encoder switch red, as in past tense, which is also initialized to false. So initially they have both the same value. And I've added two booleans, static, running, and stopping, which I initialize to false. So the first time we go into the loop, they are set to false. Now, a quadrant and step, we already had that in the last part, they are no longer initialized to 0. That's no longer necessary. Why? We'll see in a second. So, to the added code, I've here added an if statement. So, if we are not running, we compare the status of the encoder switch with the last red status of the encoder switch. And if that's not equal, that is, the switch has been pressed, we memorize what's the actual state of the encoder switch, and we start with our movement in quadrant 0 with step 0. Yeah, the initialization of these variables happens now here. And our next step will be immediately, so now at the value of millis. And we are running and we are not stopping. So if we are running and if we are not stopping, which we are not, we initialize that with false, we again compare the speed encoder switch with the last red value of that switch. And if that is different, again, we activate or we set stopping to true. So we want to stop. We cannot immediately stop. Remember, we have to go back into our up position, but we want to stop. Else, if we are stopping and we are in our movement in the quadrant 0, at the step 0, so at exactly the upward position, or that would be set down below, then again we memorize the last state of the speed encoder switch, and we set running to false. We stopped running, and the next time we enter the loop, we are of course again looking if the button has switched again, has been pushed again. Please note that when I say stopping, or we go into the stopping state, I don't memorize the status of the speed encoder switch. Reason being, if that thing is moving and you say stop, 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 it takes a while to stop. It has to move into the upward position. And I don't want the next push to the button after the stop push, the actual stop push, to lead the code into that statement here again and restart immediately. So these panic switches will be completely ignored, because only if I really stop, if I really are stopping, I memorize the state of the switch. Okay, the rest is the same. That's just us going through the several steps in the 4 quadrant of the circle and giving commands to the servo, or manipulating the pulse, changing the pulse width of the PWM signal to the servo. That's it. Let's try if I can demonstrate that, ignoring panic pushes when you really want to stop the wiggle at 2 Hertz will be a little bit hard, but I do my best. You see, I click 2 times and it still stops. It doesn't restart immediately. So let's start it and try that again. Double click, but it just stops. Great. Next, changing speed. Where are the best points to do that? I mean, trivial. Start-stop is an extreme change of speed, so we can take, of course, our actual and our potential start-stop point to change the speed. And that's what it looks like. So I start here at a very, very slow pace, about 0.2 hertz, so about 5,000 milliseconds period time, to be exact 4,800 milliseconds, and then we can turn up the speed. Slowly but surely, until we reach our maximum of about 2 hertz, or a little over 2 hertz, 480 milliseconds period time. And of course, we can turn the whole thing down again. Yeah, nice. And now I can also demonstrate you the panic button a little bit better. Yeah, click, 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 click. Stop. Okay, very good. Also, we will see that in the code. If I turn now the speed up, or try to turn the speed up, and I activate, yeah, nothing happens. I'm only allowed to turn the speed up while the servo is actually running. Okay, let's have a look at the code. Okay, changes to the code. I admit I did also a little bit of housekeeping. For example, I declared that step duration 20 milliseconds as a constant, because it should never change. Anyway, I introduced 2 new constants. Quadrant steps min, so the minimum number of steps in a quadrant, and accordingly quadrant steps max. So I will modulate my speed by doing more or less steps within one quadrant. And if you put the numbers into some formulas, you get the highest speed with just 6 steps. That's the maximum speed, a little bit over the maximum speed we calculated in part 1. We get a period time of 480 milliseconds, or 2.083 hertz, and with 60 steps we get, of course, 4,800 milliseconds, or a frequency of 0.2083333. It's 333 period, irrational number. Hertz. The astute amongst you might have noticed that I worked all the time with 8 steps per quadrant, so not quite the maximum speed we calculated last time. That was just an error on my side. Forget about it. We can now turn the volume up until 6. Also note, this is the smaller number here is the highest speed, and the larger number here is the lowest speed. Any other changes? Only in the loop. I'm using now that speed encoder position red variable, and I no longer initialize it. By the way, I'm also using, of course, that volatile int speed encoder position. How that is set in the background by interrupt routines, again, watch the video about debouncing those rotary encoders. Where were we? So I'm using that now, and if we go into the running state, I'm recording the actual speed encoder position into my speed encoder red, ignoring everything, turns off the knob before we got the wiggle running. And if we are running and if we are not stopping, I added this part here. So if the speed encoder position is no longer equal to the speed encoder position red, so somebody turned the knob, and remember, we're in the first quadrant, numbered here 0, or in the third quadrant, numbered here 2, and we are at step 0. Yeah, so we are at the top or the bottom position, speed almost zero, or zero at one point, again. I increment or decrement my steps within the quadrant according to the clicks I turned my rotary encoder. And then I, of course, remember in speed encoder position red, the speed encoder position I just processed here. And then I just, housekeeping, if I'm below my minimum, I set it to the minimum, my quadrant steps, and if I'm above my maximum, I set it to the maximum. And that's basically all. Oh, with one little exception. Just out of curiosity, I'm printing here out to the serial port the my servo signal, so the pulse width of my PWM signal I'm setting. And can we see that somewhere? Yeah, we can see it here. Let's run that thing in the background. And you do see, yeah, it's a perfect sine wave. Everything is all right. I just did that out of curiosity. I will delete that line immediately. We really don't need it. That's it. That brings us to the second and last parameter we want to change, and that is the amplitude of our sine wave. Unfortunately, there is no single best way to do that. I mean, if you change the amplitude, you also change the angular speed. So the best points would again be, the ones we already used to change the speed. However, if we are at a maximum amplitude and would change to a lower amplitude, we would do a jerk. So what are the 2 points where you can change the amplitude and never get into that trouble? That's, of course, when we are crossing zero, when we are in the middle position. So these 2 points here. However, we are still changing the speed. So we have a little jerk here. But maybe we can soften up that problem a little bit by limiting the amount we change the amplitude each time we pass through these 2 points. So let's do just that and change the amplitude at these points, but limit the change. And again, that's what it looks like. So let's start the whole thing, and I start with my slowest speed and now also with my smallest stroke. So let's speed up things first so we don't get bored. Fast enough. And now let's increase the stroke until we reach the maximum. And let's turn down the stroke again. Wonderful. Let's have a look at the code. So, changes to the code to achieve this enormous feat. I have a new constant here, servo stroke step, and that's basically the maximum or the change in the PWM pulse width per quadrant, or to be exact, per quadrant 1 and 3. Remember, we want to limit that change so we don't get any jerks. And of course, I'm now using this already existing volatile int stroke encoder position. Again, that's set by an interrupt. Watch that debouncing rotary encoders video. Anything else? two new variables here. Servo stroke max, yeah, we already had that, 180. And servo stroke min is 20 microseconds pulse width. And I initialize my servo stroke with the servo stroke min. So we start with a really small wiggle. Why are these not constants like the other variables here, quadrant steps min and quadrant steps max? We will see in part 3, but they could be constants. Anyway, only other changes now in the loop, of course. I'm no longer initializing the stroke encoder position red. I don't need that because I do that as soon as we switch to running. So then stroke encoder position red equals stroke encoder position. And then when we're running and we're not stopping, I have another if statement here. So if the stroke encoder position has changed and we are in quadrant, C++ numbering 1 and 3, so quadrants 2 and 4 of the circle, mathematically speaking, and we are at step 0. So we're exactly crossing through the 0 points of the function and our servo arm is in the middle position. Then if the stroke encoder position is larger than the red stroke encoder position, servo stroke is servo stroke plus my servo stroke step. So it doesn't matter how much I turn my rotary encoder, I only increment by that servo stroke step. And yeah, if that is smaller, so I do a counterclockwise turn and try to tune things down, then a minus. Of course, I record my encoder position again in stroke encoder position red. And I make my safety checks here if I exceeded my servo stroke max or fall below my servo stroke min, in which case I assign servo stroke min, respectively servo stroke max. And that's it. And that's it also for today. We have now total control of our sinusoidal motion of the servo, so amplitude and frequency, and we can start the motion and stop the motion, and that would be it if we are just talking motion control in a very narrow sense. However, there are some things that are annoying me about that solution. Number one, every time we repower the Arduino, we start with this tiny, wiggly, uninteresting motion. Maybe, just maybe, we wanna save a certain set of parameters. So the next time we start up the Arduino, we are back in, with a certain frequency and with a certain amplitude. That would be nice. Not really, as I said, motion control in a more narrow sense, but in a real-world application, that would be useful. And the second thing is we have still some constants here in the program, which I don't like. For example, where's the middle position of the servo and what's our maximum stroke? Let's say that servo dies at some point and you have to replace it. The next servo will need different parameters. So it would be nice to have a function to calibrate all that stuff. But we will do that in a third part. Till then, bye.